Following, we will have a look at differential amplifier. First, we will look at the generalized form of a differential amplifier with two inputs and two outputs. In that case, we have the following circuit. We have a load resistor RC, then we have a transistor Q1, and we will have a feedback resistor for better temperature stability, RE, and we have a mirrored way with also a transistor and another load resistor. We have the transistor Q2, load resistor RC2, here we have RC1. We have a second feedback resistor RE, and these two parts we have connected to a power supply plus UB, and we have a way with a current source for better stability to a negative power supply minus UB. With the currents I1 and I2 and IQ, and with the voltages for the output UA1 and UA2, and the input voltages U in 1 and U in 2, we will get the resulting drawing for calculating the amplification of this circuit. With a view to calculate the common mode gain, we will have a look at the equivalent circuit diagram of a differential amplifier. Equivalent circuit diagram of a differential amplifier. I use a small signal equivalent circuit model for a transistor in a simplified form to draw the circuit diagram of the differential amplifier. My model uses only a resistor at the base of the transistor and a current source at the collector of the transistor. So for this model, we will get a differential amplifier model like this. I have an RBE1 from the first transistor, then we have the resistor RE, this RE is for negative feedback and stabilization, and we have the current source, with the resistor RC at the collector, and at the opposite side we have the symmetrical circuit, also in RE, the base resistor RBE2, and the current source, with the collector resistor RC. So that's our model. Now let's have a look at the currents. We have the input current IB1 and another input we have IB2, and the collector current is IB times beta 1 for the first transistor and IB2, of course, multiplied by beta 2, and we have the current ID and also we need some voltages. We have the input voltage UE1 and UE2 and the differential voltage between the two inputs UD. And also we have voltages, signal voltages at our collector resistors. That's the output voltage UA1 and UA2. So that is our equivalent circuit diagram of a differential amplifier, and we use this diagram to calculate the mode amplification, the common mode rejection ratio, and so on. With this model we can calculate the complete differential amplifier. Following we will calculate the differential amplification of our circuit. Now we have UD equals IB1 times RBE1 plus ID times 2 times RE minus IB2 times RBE2. And the second equation, UA1 equals minus IB1 times beta 1 times RC. Let's say beta 1 is equal beta 2 is equal beta 0, and ID equals IB1 times 1 plus beta 0 equals minus IB2 times 1 plus beta 0. And so the result VD, the differential amplification, equals the definition UA1 over UD, that's minus UA2 over UD, that's minus 1/2, and beta 0 times RC over RBE plus 1 plus beta 0 times RE, and that's about minus 1/2 times RC over RBE over beta 0 plus RE. So we will see the amplification increases in case of greater RE and in case of less RE. So in case of paired transistors or transistors in an integrated circuit that have the both equal characteristics, we can make RE to 0 ohms, so we can forget RE, and we see we have to use a very high RC, and the highest RC we can use is a current source. So in real circuits, RC is exchanged from a classic resistor to a current source.